Hello, this time we're going to consider a collection of vectors that are parameterized by two real numbers. And we will try to examine and obtain a collection of two vectors spanning this set. Okay? Thus proving that W is indeed, in this case, a vector space, subspace of R3. But for that, well, let's start like this. Let us examine in detail the defining condition of W. So, you have that a vector x, y, z of R3 is in W if and only if we can find S and T such that x, y, z is equal to t minus s, that's just by the condition, 2t plus s, and 3t plus 4s. But now, what I'm going to do is make a decomposition. What I have here, I'm going to write it, right, in the following form as t 2t 3t plus negative s, s, 4s. Now use a scalar multiplication to factor that t and that s. So I have t times 1, 2, 3 plus s times negative 1, 1, 4. Okay, well, what is this saying, right? This indicates that W, right, is the spanning set, well, is the span of the following collection of vectors. 1, 2, 3, plus, no, not plus, I'm sorry, comma, negative 1, 1, 4. Why? Because what we're saying here is that any vector in W may be described as a linear combination of these two vectors, right? Of these two. So with this, well, all that we're doing is recasting the definition of the span of a set as a subspace. Recall that the span of a set like this one, 1, 2, 3, comma, negative 1, 1, 4, is a collection of linear combinations. What linear combinations? Well, those for which x, y, z in R3 such that there are A and B real, such that we have x, y, and z is equal to A times 1, 2, 3 plus B times negative 1, 1, 4. Moreover, we have a different formulation of this W. Also, we see that W is nothing else but the range of the following matrix: 1, 2, 3, negative 1, 1, 4. Why the range? Well, because the range is described in the following fashion, is the collection of all those y's as vectors in R3 such that there exists an x in R2 such that we have 1, 2, 3, negative 1, 1, 4 times x equaling y. In other words, we can characterize W as the spanning set of the columns of this matrix. And that's nothing else but the range of that matrix. Now, there might be some level of confusion in the symbols that we're using, right? We're seeing T and S, we have A and B, and we have these vectors Y and this vector X. But those are just dummy variables. Remember, when you talk, for example, in integral calculus about this integral, well, this integral represents the same object as this one and as this one. They have the same information. All that changes is the variables that we use to define them. It's exactly the same thing that is happening here. In this definition, we use T and S. In this definition, we use A and B. And in this definition, we use a condensed version where we say, well, y is really a vector, y1, y2, y3, while we say that x is another vector, x1 and x2 in R2. Okay, so keep in mind that we may use different symbols to actually denote the same entity. In this case, the collection of vectors W, which we showed that it is a subspace simply by indicating that is the span of another set. Okay, so I hope that you like it. Take care.